Okay, let's start. This is the second from last laboratory. So, not the laboratory 12 on GMM. And it's, as you can imagine, we are getting near the end, so they're becoming a bit more complex, unfortunately. I would be happy if I could give you the complex one at the beginning of the course, but that's unfortunately not possible. So, model on Gaussian mixture model. Now, as I said, it's more complex, but we will try to reuse most of the things we already wrote to minimize the amount of additional code that we need to write. Of course, even reusing the previous code correctly is not necessarily trivial, but let's try. To use the GMM models for classification, we need to do several things. We need to train the model. We need to be able to make inference with the model. To make inference, we know for sure we need to compute the log, the density of the model, and in particular the log density of a GMM. To train, we will need to implement the M algorithm and the LBG strategy. So the laboratory will involve all these steps. Let's start with the simplest one, writing the log density of the model. The log density of the model is what? Well, this is the definition of the GMM. So if we have a GMM with means, covariance matrices, and weight, we can write a log PDF function that receives the GMM, receives, as usual, a matrix of samples. As usual, we work with a matrix of samples, but if you prefer, you can work sample by sample and then putting everything together at the end. But as for the Gaussian model, we assume that the input of this function is a matrix of samples, and the output should be the corresponding densities for all the samples. So we have x1, x2 through xn. Here we will have log GMM of x1, given the parameters, theta. Then the second value will be log GMM density for x2, given the parameters, up to log GMM density of xn, given the parameters. How we represent the parameters? You can do what you want. You need to represent for a GMM with m components, m means m covariance matrices, and m weights. The way we use in the solution that you have online, and that's what there will be the format that will be assumed in the laboratory, but of course you can change it if you don't like it, is to put the GMM information in a list component by component. So for each component, we have a list with m tuples. Each tuple are the parameters of one component: weight, mean, and covariance matrix for that component. So these are the set of the parameters, slightly different from how we represented them in class, but the same information. Now, the first step is implement this log PDF GMM that will take the role of the log PDF GAU when we will do inference. This should compute the GMM density. So one possible way is to apply the definition. Notice that the definition, if you apply it blindly, will compute exponentials of values, so we compute densities of Gaussians that we know will saturate. So ideally, we would like to do this remaining in the log domain, so without taking the exponential. How can we do it? Well, since we are a few, let's try to figure it out. Maybe that will help you to implement it. How can we compute the log density of the GMM? If you remember, when we introduced GMM, we said we encountered, even if we didn't call it a GMM already several weeks ago. When did we encounter something that looked like a weighted sum of Gaussian? Go back to the laboratory on Gaussian models. At some point, you had to compute what? Class posterior probabilities. To compute class posterior probabilities, For a model with 3 classes, with the Gaussian model, what were you doing? You were computing the class conditional densities for class 1, for class 2, and for class 3. And in particular, you were taking the log of this, do it for all the samples, so for sample x1, then for sample x2. So you were computing a matrix of class conditional densities. And then you were adding the log prior for the class. This was a matrix of class and feature joint density. And then you were computing the marginal. How were you computing the marginal for this? We saw how to compute it. How were you computing it? Not directly sum, because there is the log, using the log sum x, but yes, the idea here was take exponential of this, sum, and take the log in a robust, numerically robust way. And this was the log density. But what is the log density in this case, if you write it mathematically? It's a sum of prior probability times Gaussian density. So this is the marginal of what? We can interpret this as this is the density also of a GMM model where these are the weights and these are the components. So the marginal for our MVG classifier was the density of a GMM, which had the priors of the class as weights and the Gaussian of each class as components. So we could see that as a GMM, which means that we can reuse the whole code we wrote to compute that marginal here to compute the Gaussian, the GMM density. So we do the reverse. Here we have a GMM with weights and components. So we first compute the log condition, the component conditional density. So this time we call it cluster conditional. But the fact that we call it cluster or class is just for us to understand what we're doing. But from the mathematical point of view, or from the code point of view of the code, whether we call this class or cluster makes absolutely no difference. So we compute the matrix that contain cluster conditional densities with the Gaussian of the model. We add the log prior, that in this case is not the class prior, but is the weight of the component. We can call it weight. We can call it class prior. Again, from the code point of view, it doesn't matter. This time the weights behave as a cluster prior probability, so we add the log weight. This will be the log joint density for the component and the corresponding feature. And then log sum x on this will give me the log marginal of this. But the log marginal for a GMM, where the marginalization is taken over the component, is exactly the density of the GMM. So the code that you were using for the MVG classifier to compute the marginal that then was used for class posterior is exactly the same code that you can use to compute the marginal, the GMM density, which can be interpreted as a marginal of a model which has cluster components, prior on the cluster, which are the weights, and Gaussian associated to each cluster. And then we are marginalizing with respect to the cluster information, to the cluster label. So it's exactly the same code. If you understood, of course, if you don't like it, you can start again from the definition. If you understood this, you can go back in the laboratory in MVG, copy paste the code, and you've done with your log PDF density, if you copy paste correctly. So this is how we can implement the log marginal. Is it clear? Do you think it's doable? Or is it clear how to do it? So what you have. So hopefully this will not be a big issue. If it is, of course, ask me. But hopefully this will not, because again, it's the same steps that we were doing to compute the marginal when we were computing the marginal for the MVG model. Now, once we have, and here you have also the steps, so the things that I told you are repeated here, so with the steps, with the guided steps. So you have also an indication on how to build that matrix if you don't remember from the lab. Of course, if you remember from the previous lab, that's better, but if you don't, You have here how to do it, even exploiting the previous laboratory results. So try to figure it out, and then if you have issues, you have some steps that you can ask me. Then, once you have done it, you have, as usual, some synthetic data to test your results on that you can use to check whether your PDF is giving you the correct values. Then, once you've done this, let's get to the bulk of the laboratory, so the training of the GMM, which is something that takes a bit more effort, and it's probably the highest effort part of this laboratory. The M algorithm. The M algorithm, which is this called from expectation maximization, we don't see why, but essentially it's an algorithm that is more general, that applied to the GMM gives exactly the procedure that we have seen, requires that given an initial set of parameters, or using the notation of the lab, a GMM 0, I don't know how I called it, or GMM T, because I was using T here, will produce an updated GMM T plus 1, whose likelihood on the training set will be at least, will be greater or equal than that of GMM T. Equal if we are at convergence, greater if we didn't find a local saddle point of the likelihood, which will typically be a local maximum. So let's see how to do one iteration, then we will discuss how to initialize the first iteration. So let's figure how to do from a given GMM, how to get an updated GMM. We have said that we have two steps. The first is called expectation step, or is step for short. And in this step, essentially, what we need to do is to compute the cluster posterior probabilities. The cluster posterior probabilities, again, I suggest to arrange them in a matrix. So you have sample on the row, x1 on the column, sorry, x1 through xn, and the rows refer to the component Gaussian 1, Gaussian 2, up to Gaussian. Let's say you have, here it doesn't say, let's say you have m components, Gaussian m. Now, do you know how to compute this matrix of cluster posterior probabilities? Do you know how to do it? How? Yes, we can again reuse the code that we used for the MVG. If rather than calling the classes, we call them cluster, and the priors, rather than calling them priors, we call them weights, this is exactly the output that we would have when we were using the MVG for classification. There it was class posterior probability, here now it's cluster posterior probability, but the model is the same. For each cluster, we have one associated Gaussian with a prior probability that is the weight, and we are trying to compute the posterior probability for the cluster. So we can proceed exactly as we did for the MVG classifier. So here we are considering a single dataset. We are fitting a GMM to one dataset, but we can reuse the code that we were using for classification for the MVG. There, the dataset was assumed to consist of samples of several classes. Here, we have a single dataset, typically of one class with several subclusters. So the clusters here take the role of the classes in that laboratory. Then when we use the GMM for classification, we will introduce classes also here in this laboratory. But let's take things separated. Then, as you have learned, hopefully in the previous years, once you pack things into functions, when you move to the higher level, you don't care about the lower level because that's hidden inside the function. So I will try to follow the same approach in the explanation. So now we are optimizing a single GMM for a data set, which will typically be the samples of one class, but we treat this data set as it's comprised of clusters. And we can reuse the MVG code, treating the class of the MVG become the clusters of this model. So essentially, that means that we will take our x1 through xn. We compute first the vector that contains, let's take one of these and enlarge it. This will be a vector that contains the log normal for sample xi with the Gaussian component 1, then the same log normal for sample xi with the Gaussian component 2, and so on. So each of these vectors will contain the cluster conditional densities, which, as we did for the MVG, each row of this vector corresponds to one component, so can be obtained in a single shot by calling the log PDF Gauss function, giving the matrix of samples and the parameters of the corresponding Gaussian. Remember that this will compute exactly the log densities for all samples with a given model. So we can reuse the Gaussian laboratory functions to compute the rows of this matrix directly, or you can reuse the code of the laboratories of the MVG as you prefer. You can copy from there, you can copy from here, but the results is the same for all the Gaussians. Then to each of these, we now need to add the log weights. That means we take the vector of weights, we take the log, we treated this as a column vector, and then we add it. Broadcasting will add it to everything. This will be the matrix of log joint. Then, through log sum x, we take the matrix of log marginal, which, by the way, is exactly the code that you should have implemented in the step before to compute the PDF of the GMM. So we are not even introducing anything. If you have done the previous function, you already have the code up to this point. Then to compute this into posterior, you need to remove the vector of marginals from the matrix of joints row by row, as you did in the MVG. This will give you log posterior, log cluster posterior. You take exponential, and you have your class posterior probabilities, your cluster posterior probabilities. Is it more or less clear? Okay, once you have done this, we have the matrix that contains all gammas. We call these gammas. Okay? So I refers to the sample I, G refers to the component G. Now the next step is, for each Gaussian, we need to update its parameters. So for each component, we need to compute the updated mean, the updated covariance matrix, and the updated weight. Which means that now, here this we will do with a for loop, Gaussian by Gaussian. We will take the gammas of that Gaussian, so we will slice this matrix of gammas in rows. Each row refers to one Gaussian. So for example, if we take the first row, we have all the gammas of the first component. These are the samples, and this is G equal to 1. These are the weights that I should use to weight the samples when I update the parameters of the first Gaussian. So the row of the first row of this matrix contains the weight that I should associate to each sample when I computed my weighted mean and my weighted covariance matrix. So now we use these weights and use them to compute. The sum of the weights is the zero-order statistic. So the effective number of points associated to the Gaussian, which can be fractional, so I cannot say number of points. It's an effective number. It's called, that's why we call it zero-order statistic. It's not exactly a number of points, but it behaves like a number of points. The first-order statistic, that is the weighted sum, and this second term, that is the second-order statistics, that is related to the dot product xi transpose, and then from those, I apply this expression to compute mean, covariance, and weight of the samples. Or if you prefer, if you don't like this expression, you go on the slides, you take the expressions that we gave explicitly for the mean, covariance matrix, and weights, and you apply those, which are the same. I suggest you get familiar with this, because these are, well, essentially, if you were to implement this for real, these are more efficient ways of doing it, because going through the original definition requires that you loop over the data twice. One to compute the mean, and then another time to compute the covariance matrix, which for our data is not a problem, but if you have lots of data that don't fit in RAM, it's a problem. While if you compute the statistics, you can compute these values in one shot over the dataset, and then you have everything you need to compute mean, weight, and covariance matrices. But as you prefer. The important thing is that you got those numbers out. You repeat it for all the components, and that gives you the updated GMM. Things to take into consideration. Well, here there are the instructions that I just gave you. Remember to use the log sum x function whenever you need to take sum of exponential of something. Again, computing log posterior. These are the same instruction of the MVG. So these things are things that I rewrote, but that you should already know. And then for the statistics, you have a weighted sum and a weighted sum of dot products. It can be done exploiting broadcasting and exploiting matrix vector multiplication in a proper way. You can try to figure it out. If you don't figure it out, just write a for loop over samples and that will be fine. Then if that's too slow for your project, you can just, once you have verified that your function works, you can swap it with the one that you have online, and that will be fast because it does it in an efficient way. Maybe not the most efficient, but still quite efficient way. Then, this is one iteration of VM. Then what we will do is repeat the iteration several times. So we will not stop with one iteration. This tells us how to go from theta t to theta t plus 1. We actually want to go from theta 0 to theta star. This will be through several steps. So theta 1, theta 2, up to some stopping criterion. So this is one iteration of the algorithm. We need to iterate this procedure, estimate posterior, and update the parameters several times, starting from an initial point. So the whole procedure, my suggestion is to skip it in two functions. One function given, well, I don't remember if I did it in the solution, but one function that given the current a set of parameters gives you the update, and then something that loops several times over those. I think the solution online doesn't do this separation. It's, the whole EM is in a single function, but maybe this is easier to implement in it this way. So, given some starting point that I will give you for the moment, we need to reach some final point. Final means that we will need to decide some criterion to stop our iterations. When should we stop? Well, the idea here is to stop when the likelihood, when the log likelihood doesn't increase enough from one iteration to the other. So if you monitor the log likelihood, you will see that the log likelihood will do something like this. It will start increasing, and at some point it will keep increasing, but more and more slowly. So when the difference between two subsequent iterations is very small, we stop our iteration, assuming that we have reached a plateau. How we do that? Well, every time we run an iteration, we compute the log likelihood. What is the log likelihood? Well, once we have our parameters, theta, we can compute the density of the GMM for all the samples with theta. This will be a vector of log densities for all the training samples. The log likelihood is defined as the sum. Sorry, here it's missing a log. The log likelihood is the sum of this marginal. So you will take, whenever we update the parameters, we compute the PDF for the density for the training samples themselves. We sum those values. That's the log likelihood we want to monitor. Now, two considerations. We will not use the definition of log likelihood as the sum. What we will actually monitor is the average increase of the average log likelihood. So we'll take our likelihood and divide it by the number of samples. Why? Because the log likelihood depends on the number of samples. If I double the training samples, my log likelihood will double with the same parameters if I copy them. So take the data set, duplicate it, and compute the log likelihood for the duplicate for the data set that contains the original and duplicated. It will be twice the original log likelihood. However, we want a criterion that does not depend on the number of samples to stop our iterations. To have a criterion that is reasonable regardless of the number of samples, rather than looking at the increase of the log likelihood, we look at how much the log likelihood the average log likelihood per sample increases from one iteration to the other. So the criterion will be based on the average log likelihood, and we will stop when the log likelihood between two subsequent iterations goes below some threshold delta. And then these I put in parentheses because we are not going to do it, but just to know that the way you will implement it is probably calling the log PDF GMM for the samples once you have updated the parameters. We could avoid calling this function at all. The things that we compute during the GMM EM steps are enough to also give us the log likelihood for the previous set of parameters. So when we go from theta t to theta t plus 1, the things that we need to compute theta t plus 1 allows also to get for free the likelihood with the parameter theta t. So now that it can be done in a much more efficient way, but again, probably we will not do that, so just ignore this note. If you want, you can read it, but if you skip it, everything will work nicely in any case. But in real implementations, you wouldn't find the PDF recomputed after each update of the parameters to monitor the log likelihood, because there's no real need to do that if you write your computations properly. Or to say in another way, if I need to compute the log PDF with parameter theta t, then updating the parameters to theta t plus 1 is almost for free, because the most expensive computations I've already done when I were computing the log density. Now you have an example where you are giving an initial GMM, so your theta 0, because for the M we need an initial GMM, so you have an initial GMM you can try your model on. Pay attention to this that is written in red. If your log likelihood decreases at some point, even by a very small amount, then there is a very, very, very good chance that your algorithm is wrong. I've yet to see an implementation of this where the log likelihood decreases and the implementation is not wrong, even by tiny amounts. So if it decreases, then there is a problem with the implementation. It should, at worst, remain stationary, but it will not decrease. Then, once you have implemented this, you have done most of the work, but you get our GMM working, we still need to be able to train it from scratch. I'm not going to give you an initial GMM for the project data. So we need to figure out how to do that. For that, we will use the LBG algorithm, which was how we start from a GMM and we split its components. So what we will do, we start with a GMM with one component, and the GMM, that's what it is, one component GMM, which is actually a single Gaussian model, weight equal to 1, so it's a Gaussian. It's the Gaussian, the maximum likelihood Gaussian fit for that data. So we know how to compute the maximum likelihood solution without EM. For the one component, we know exactly how to do this. So we compute this by fitting one Gaussian to the dataset. Then we start with our algorithm. We fix the number of target components, which for this algorithm will typically be a power of 2. So for example, let's say we want to reach a Gaussian model with 16 components. What we will do? We'll take the components of this Gaussian and split them. So this will be a GMM with a single component. We will create and let's go like this, split. The split will transform this into two components, one with half weight, the weight was 1, so half of that is 1, mu plus some displacement 1, so let's call it mu1 because it's the component 1, and covariance the same, and the second component will be 1/2 mu1 minus displacement C1. So now we have a two components GMM. This GMM is not the maximum likely solution for our data. It's not optimized for the data because that's a split of a one component GMM that was optimized. So this was a maximum likely GMM. After the split, we don't have a two components that maximize, whose parameters are a local maximum of the likelihood. So we'll now run the M algorithm starting from this component, which will iterate until our delta log likelihood becomes lower than some threshold. And the output will be two components GMM that corresponds to a local maxima of the log likelihood for the training set. The M algorithm finds a local of the log likelihood. Now, that means we have a new GMM, a GMM with two components. Now we apply the split again. So now we have a GMM, let's say, with weight 1, mean 1, covariance 1, and weight 2, mean 2, covariance 2, which have been changed because the M changed them. We'll now split this into 4. The first will have W1 half, mu1 plus a displacement 1, because the displacement we see depends on the component itself, so the displacement will change from component to component, and C1. And then the second one will have same thing minus the same displacement C1. And then the third component will be a split of this. So we'll have mean 2 plus some displacement and then C2. And then the last component will be the second split of the second component of the original GMM. So this will be our 4 components GMM. Now this is not optimal for the data, so we run EM and we'll obtain a 4-component GMM that has a maximum likelihood solution for the 4-component models. Then we keep this, we split to 8 components. EM is a 8-component GMM maximum likelihood, and then as you can imagine, we split further to 16 components, and then EM 16 components maximum likelihood solution. So we repeat until we get the maximum likelihood solution for the number of components that we want. How we select the number of components, we'll see in the project. We will use cross-validation, so we'll try different values and see what happens. How we select the displacement, D, we said that a reasonable thing to do is if we have, let's throw it here. If we have one direction over which there is a strong large variance, means that it's a direction over which there is large variability in my data. So I can imagine that heuristically this may be due to different subclusters that were covered by the same Gaussian. So it may make sense heuristically to try to divide these into 2 components in a way that will guide the 2 components to cover these 2 subclusters. Of course, this is an heuristic. It's not necessarily true. But let's apply this that works well in practice. This means that for each component, the displacement will be over the direction corresponding to the eigenvector, eigenvalue. So we take the covariance matrix, we compute eigenvectors and eigenvalues, we take the leading one. By how much should we move? We move by a fraction alpha of the standard deviation over that direction. So the standard deviation measures how spread are the data. We move by a factor that is proportional to the standard deviation. Why we don't move by an absolute factor? Because if the standard deviation is larger, it means that to get a similar effect, I need to move farther than if the standard deviation is smaller. If I want to have the peak of the 2 new components in a relative position that is similar, I need to move by an amount that is proportional to the standard deviation. By how much? By a value alpha that for the laboratory, I think we fixed to 0.1. I think it's said somewhere. If it's not said, look on the solution online, but if I remember right, it was 0.1. Again, this may affect the result. For the laboratory, we don't check how it affects the results. We just use 0.1, that is a reasonably good value to have steps that are not too small, but not too large either. Final considerations, this is what you should obtain when you put everything together. This is training 1 GMM. Then couple of things to pay attention to, because that may affect the project data when you have more components. We said the GMM has the risk of becoming degenerate. The model is free, has multiple Gaussian. We said that this allows the model to put one Gaussian above a single point and shrink its variance towards 0. This will increase our likelihood. So if we try to maximize the log likelihood, we will actually fail, because we will find a degenerate solution. Now, typically, we will not, if we don't have too many components and we start with reasonable initialization like the LBG, we will not get into this problem. But even if we start with reasonable initialization, if we keep adding components, at some point we may end up with this problem. Possible way is to stop when there are too many components. Another way is to try to monitor when this happens and then change the initial solution so that we may end up in another point. Another way is to try to avoid the pathological solution by avoiding that the variance can go to 0. If the model decides to put a matrix component over one point, but then it cannot shrink it indefinitely, we may have a component that is not well reflecting the data. Typically, since it covers only a single point, its weight will also be very small, so we can post-process and prune it. And in any case, it cannot lead our likelihood to infinite. How can we do that? We can do that by constraining that all the eigenvectors of the covariance matrix are greater or equal than some threshold value. If they are all greater or equal than some threshold value, then it's not possible for the model to have 0 variance for some direction. So it cannot become degenerate. There are better strategies than this, but we see this because it's the easiest we can do. We can do better, but let's focus on this. Now, why we focus on this? Because this is fairly easy to implement. It's fairly easy to implement because we can show that if we start our EM iterations with covariance that follow this assumption, so whose eigenvalues are all positive, then we can obtain a solution that increases the likelihood. So it respects the fact that at each step we increase the likelihood in a simple way without having to modify our EM. How? Well, if theta t has all eigenvalues greater or equal to psi, then we run our EM algorithm, we compute theta t plus 1, then we take all the covariance of these matrices, all the covariances of these components, we compute their eigenvector decomposition, and if some eigenvalue has gone below the threshold, we reset it to the threshold itself. So the EM algorithm will give us a solution that may be not optimal, may be degenerate, but we can compensate, we can fix that iterations in a way that overall it will still be a proper EM algorithm and will still increase our log likelihood. How? Well, once you have computed by EM your covariance matrices, you will decompose the covariance matrix. All the eigenvalues that are, here we use the singular values because it's the same thing. They are positive semi-definite matrices, so we use SVD or we use eigenvalues, it's the same thing. All the singular values, so the eigenvalues that are lower than our threshold are set to the threshold, and then we build the new covariance matrix that has the same principal axis as before, but the updated, the fixed eigenvalues. So essentially, along those directions where the covariance was shrinking too much, we enlarge it again to the minimum value that we allow, okay? And here is the code to do it. So you just need to plug this code afterwards. The only thing you need to pay attention to is that to ensure that our algorithm still works and that each iteration have an increase of the likelihood, also our theta 0 must follow that assumption, which means that when we run our LBG algorithm, we start with one Gaussian fitted by maximum likelihood. That Gaussian must also respect the criteria. So when we train the initial model with one component, we need, even if we use Gaussian model, the ML Gaussian fit, so we compute the mean and the covariance of the data. After we have computed the covariance, even for that model, we need to apply this procedure to ensure that the covariance that we compute is the maximum likelihood subject to the constraint that all eigenvalues are greater or equal to psi. So this is an equivalent of a constrained maximum likelihood, finding the maximum likely solution under the constraint that all eigenvalues must be greater or equal to psi. And the code is the same. You just need to apply it also to the first model, with one Gaussian. Then, as I said, if you want, you have instruction how to implement the models that have diagonal components or tied covariance components. That's, again, something fairly easy. Once you have the full EM, it's just a matter of diagonalizing your covariances or averaging them properly. But, of course, as I said, this is optional, so I will not ask this in the exam. But if you want, you can try it. And then, once you've done this, the last part will be using the GMM for classification. The GMM for classification, once you've done all the rest, should be fairly easy if you have written the code, if you have divided the code in functions. So if you have a function for training, if you have a function for computing the PDF, etc. If you didn't, it will be a hell to implement this part. If you split it in functions and you have a function for training a GMM, a function for computing the log density for samples, then it's trivial because we can take, again, the MVG code, swap two functions, and we have everything implemented already. How? Well, how do we do classification? For classification, we set a different GMM per class, which means that we have our three classes. We take the samples of those classes, so we have the original data set, we split it into the samples of each class, then independently we fit a GMM to each class. If you have implemented properly the previous code, it's just a matter of calling that function with the, if you have three classes, with the three sub data sets that corresponds to the classes. This will give three different GMMs. Notice that it's also easy if you want to have GMMs with different components. You just specify the number of components to be different in your training function, you call it, and you have GMMs with different components. Once you have the models, how do we make inference? Well, if it's a multiclass, the inference is the same as for the MVG, but rather than computing it's the same in which sense? That in the MVG we had three steps. Compute the matrix of class conditional, then from this, the joint, there was the class conditional plus log prior, then the marginal, and then the class posteriors, okay? All this code remains the same. What changes is just how to compute the class conditional. The class conditional is what? I need to build a matrix where each column contains what? For each sample, the class conditional for those samples. So the log GMM density for the sample xi for class 1, 2, and 3. These are the parameters, the three GMM that we were getting out. If we look at this matrix in rows, the first row is what? It's the density of all the test samples over the first GMM. How can I compute this if I did the previous laboratory? What was the first step of the laboratory? If this is the GMM for the first class, the density of all, the log density for all the samples using the GMM for the first class is nothing else than the call to this log PDF GMM class. In the MVG, here you were calling log PDF GAU with the parameters of the first Gaussian. Here you call log PDF GMM with the parameters of the first GMM. Then what you get is the same interpretation, is the class conditional log density. Once you have done it for all the samples, you have a matrix of class conditional log densities. You don't care what the density was. You don't care whether it was a Gaussian, whether it was a GMM. You have the matrix of log density, log conditional densities. You need to get the matrix of log joint by adding the log prior. Then you need to compute the log marginal for the samples by log sum x of the rows, as you did for the MVG, remove that row from the log marginal from all the rows of the matrix, that gives you log class posterior. That's again the same code that we were using for the MVG classifier. Just the initial part is different because we need to create the log class condition with the GMM density rather than the Gaussian. But all the other steps are exactly the same code if we implemented it in a good way. And for the binary problem, that's even easier because your log-likelihood ratio, here it's missing a log, is just a log density between what? Log GMM for the samples x given the GMM parameters 1 divided the density for the GMM parameters 2 or 0, which is just 2 calls to the log PDF GMM function again. If you have implemented the function that does the logarithm of the density of the GMM, you call it with the test samples x, the parameters of the GMM1, then you remove the result of the same function, this time called with the same samples, but the parameter 2, that's your log-likelihood ratio. That's the same we did for the Gaussian model. In the Gaussian here we had log PDF GAU, now we have log PDF GMM. But once you abstract to the fact that you have a function that gives you the density, all the rest remains the same. What changes, you just need to plug the new function for the density rather than the previous one. Questions? Okay, then for the project, you need to repeat all these on the project data. Train full covariance models, we do only full covariance, so we do not do the special ones, with up to 32 components. Why? Because I know that if you go over 32, you will start having numerical problems, you will start having severe overfitting that you already start having with 32, I hope. But in any case, there is not much you will gain from the analysis, and it will take more time. Now, the suggestion is to try with using different number of components and even different number of components per class, and then try to relate the performance with the analysis of the dataset characteristics of the sample distribution that you saw at the beginning of the course. And then compare with the other models and start doing also some analysis on bias error plots for all the models that you have selected, one SVM, one GMM, and one logistic regression, essentially. And start comparing them by, for example, using bias error plot to see not only how they work for the target application, but how they would work for different applications, the best 3 models that you have in each category. Then next week, we will calibrate them and fuse the best SVM with the best logistic regression and the best GMM and see if we can gain something more from combining the results of all these. Suggestion for the project. Here it says to try different number of combinations for the components. Remember, if I train a 16 versus 8, and then a 16 versus 4, and then 16 versus 2 components for the 2 classes, I don't need to retrain this 16 every time. The 16 components GMM is always the same for the same class. So I train the 16 component GMM once, here, the 8 components, and then I have maybe 8 versus 8, 4 versus 8, and 2 versus 8. All combinations that I can have. I need to train the 16 only once. I need to train the 8 components for the other class only once. Those are always the same. Even better, if you train directly for 32 using the LBG, and each time before you split, you save your GMM, you will have the full sequence, because we start with one GMM maximum likelihood, the one Gaussian, then the split will give 2 components, and then EM will give 2 component maximum likelihood, then for components, the split for components maximum likelihood. If here you save all these models, you train only once with 32 components as target, and as a side effect, you also have the models with 16, 8, 4, 2, and 1. So you have all the models that you just need to test. Training can be expensive with the GMM, but actually, if you organize it properly, you need to train once per class. If you don't do it properly, then you have all combinations and you train everything several times, and that makes the number of things that you, the number of computations that you do significantly larger. Even with the efficient code, it would take some time.